Synthesis of corallidictyl D. Corallidictyl D is a spirosesquiterpene aldehyde. It is isolated from the marine sponge Arca corallifaga. Here's a picture of it. Corallidictyl D has been shown to possess the broadest range of antibiotic activity and exhibits significant cytotoxic effects against L929 mouse fibroblast cells. Here's the reference to the article in the RSC format. The key bonds formed in corallidictyl D is the CC bond, formed by a PD-catalyzed cross-coupling reaction, as well as the CO bond, formed of the cyclic ether by an acid-induced ring closure reaction. Prior to the use of the palladium catalyst in the cross-coupling reaction, ligand dissociation occurs as phosphine ligands are sequentially lost from the palladium complex, with the potential for them to reassociate. Throughout this process, the oxidation state of the metal remains unchanged. The 14 electrons in PD-PPH32 indicate that the complex is coordinatively unsaturated, which allows it to act as an active PD0 catalyst. The catalytic cycle begins with the palladium catalyst at an oxidation state of 0. During the oxidative addition step, the carbon-iodine bond breaks, and that leads to the formation of an aryl palladium complex D, where PD now has an oxidation state of 2. Then, the diazo compound C, formed from the K2CO3-mediated decomposition of the tosyl hydrazone B, reacts with complex D to produce the palladium carbene complex E. The unstable aryl palladium carbene complex E then undergoes migratory insertion of the carbene ligand, and this forms the alkyl palladium complex F. Beta hydride elimination forms the CC double bond to provide the arylated alkene G, and a PDH bond is also formed of the metal hydride. In the reductive elimination step, the base deprotonates the metal hydride and potassium iodide is also formed, and the PD0 catalyst is regenerated. This acid-induced ring closure reaction occurs under thermodynamic control because it undergoes reflux for 3 hours. In the first step, the alkene is protonated by the HCl, and the most stable carbocation is formed at this carbon. This carbon is more easy to protonate as there is an steric hindrance, so the hydrogen gets attached here. Then, the lone pair of the oxygen on the hydroxyl group attacks the carbocation, which forms a new CO bond, shown here. This also creates a chiral center. The methanol then deprotonates to form the cyclic ether with complete stereoselectivity, and the product formed is a diastereomer. These conditions were preferred over other cyclization conditions such as using NIS or PPH3 and other circumstances because those are more poorly selective as a mixture of corallidictyl C and D were formed. In the first step of this iodination reaction, the Bi3+, which is a Lewis acid which comes from the bismuth triflate, coordinates to the carbonyl oxygen of the succinimide, attracting electrons and weakening the nitrogen-iodine bond, thus making iodine more electrophilic and making it more susceptible to nucleophilic attack by the arene. And then the Wheelan intermediate is formed. The regioselectivity is at position 5, as it's the most nucleophilic position for substitution, as it is para to the isopropyl group at position 2 and ortho to position 4, receiving significant resonance activation due to the resonance from the electron-donating isopropyl group. Position 3, however, is not favored due to steric hindrance of the isopropyl groups at positions 2 and 4, and this reduces the accessibility of this position for nucleophilic attack, thereby reducing the likelihood of iodination. Thank you for watching.